we arrive at Chapter 3, Differentiation Rules, and we're going to work with this idea of the derivative. Section 1 of this chapter, derivatives of polynomials and exponential functions. In this section, we learn how to differentiate constant functions, power functions, polynomials, and exponential functions. In this video, we will deal only with constant functions and power functions. So, constant function, f of x equals c, f of x equals 5, a number. And immediately the horizontal line comes to mind, and the slope of such a line is 0, doesn't go uphill or downhill, and of course the derivative of a function at x is the slope of the tangent line at x. So we tend to think first of the slope of the tangent line, and so since that's 0, the derivative of a constant function is 0. Easy to prove. Okay, how would you prove it? Well, we'd have to think about what the derivative is, which is the limit as h approaches 0 of f of x plus h minus f of x all over h, the difference quotient, and f of anything is just c, and so the numerator is c minus c, which is 0. 0 divided by anything is 0. Limit as h goes to 0 of 0 is 0, so that's the value of the derivative. In Leibniz notation, we would write this rule as derivative with respect to x of the function, which is just the constant c, equals 0. Okay, so power functions. X to the n. Okay, so you just have x raised to a power. Those are the power functions. N is a positive integer. And so let's see what happens with different values of n. For n equals 1, then we have f of x equals x to the first, and that's the line y equals x, the graph of the identity function, and the slope of that is 1 because you always rise 1, run 1. And so for x to the first, no matter where you are actually, the derivative is 1. We could also verify this from the definition of the derivative. Limit as h goes to 0, f of x plus h minus f of x all over h. Now, we have already investigated n equals 2 and n equals 3, the squaring function and the cubing function, and that the derivative of the squaring function is 2x, and the derivative of the cubing function is 3x squared. What about the fourthing function, x to the fourth? Okay, so we set up our definition here, and we're going to find f of x plus h, which is the fourth power of x plus h, minus f of x, which is x to the fourth, all over h. And take the limit as h goes to 0. Well, we're going to expand that fourth power of a binomial, and you could use binomial theorem or whatever method to get x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. And then we're subtracting x to the fourth, and it's all over h. Of course, we will have cancellation here, and we're familiar with this event that every remaining term in the numerator has a factor of h, which of course can be factored out. And then that factor of h can be canceled with the factor of h in the denominator, giving us 4x cubed plus 6x squared h plus 4x h squared plus h to the third. And now we're going to take the limit as h goes to 0. Well, as h goes to 0, all the terms except the first term go to 0. Of course, we remember that the limit of a sum is the sum of the limits, so we could think about the limit of each of these three terms separately. And of course, x doesn't depend on h, so this is just 4x to the third. So it's 4x to the third for the derivative of the fourth degree power function. Now let's think about this. We've got several derivatives of power functions. The derivative of the first degree power function is just 1. In other words, 1x to the 0. And the derivative of the second degree power function is 2x to the 1. The derivative of the third degree power function is 3x to the second. And the derivative of the fourth degree power function is 4x to the third. So there seems to be a pattern. Okay, so we've got a 1 and a 1, and a 2 and a 2, 3 and a 3 and a 4 and a 4. And the exponents, there's a pattern with those as well. They go, as the degree goes from 1 to 2 to 3 to 4, the exponent goes from 0 to 1 to 2 to 3 in the derivative. It seems to be a reasonable guess that when n is a positive integer, the derivative with respect to x of x to the n is nx to the n minus 1. And this actually turns out to be the case. And so there's our power rule. The derivative with respect to x of x to the n is nx to the n minus 1. So there's some examples of this that we can look at. So x to the sixth, it's as if we're taking that 6 and we're throwing it down here and subtracting 1 from the 6 to make the 5 in the exponent. So 6x to the fifth, that will be the function which is the derivative of f of x for the sixth degree power function. Well, let's see, for x to the thousandth, well, that 1,000 will come down as a cofactor, and then we're going to subtract 1 from the 1,000 to make 999. So y prime, the derivative with respect to x, is 1,000x to the 999. And let's go Leibniz here. Y is t to the fourth. So the derivative of y with respect to t is, bring down the 4, subtract 1 from the exponent, 4t cubed. Derivative with respect to r of the function r cubed is 3r squared. In general, Here's the power rule. Derivative with respect to x of x to the n is nx to the n minus 1. The power rule enables us to find tangent lines without having to resort to the definition of the derivative. We can use the power rule, and we don't have to think about the limit as h goes to 0 of f of x plus h minus f of x all over h. It also enables us to find what are called normal lines. The normal line to a curve C at a point P is the line through P that is perpendicular to the tangent line at P. Because if you can get the slope of the tangent, you can get the slope of the perpendicular. They are negative reciprocals. And if you can get the slope and get the equation of the normal line, if that's what you want to do.